When we have our questions that see forces either acting together to move an object or against each other to keep it in place, we may expect to find this on a horizontal plane or a vertical plane, as we may have seen in the connected particles and pulleys videos. However, it is possible that you'll find this to be a combination of the two in your question, i.e. that your particle or your block is instead on a slope, as we can see here in this example. Per any question that may then involve F equals ma, the equation that force or the resultant force equals mass times acceleration, as well as your Suvat expressions. As with any of those questions, you will need to label on your forces and therefore work out what the overall force is going to be. However, here, this may just then get a little bit more complicated. Firstly, because we're now going to have to work with components of forces. I'll explain what that means in a second. And also because we're going to introduce this other idea of friction. Now, friction is something that could come up in those connected particles and pulleys questions that we mentioned before. But we're just going to discuss it here, and then the principle should be applicable to any type of question like this in mechanics, if you were to come across it. So to begin with, we have this block here on a slope that's at a 26-degree angle, and we're told that the 10 Newton block is in the point of sliding down the slope. Now, if it's on the point of sliding down, that means it's not sliding down yet. That means it is in equilibrium, and if it's in equilibrium, then the forward force equals the backward force. In this case, the forward force, the force that is ultimately trying to make it move down the slope, will be a component of the weight. Now we're told here that it has a weight of 10 newtons, so that would be acting straight down. Just as a reminder, weight we get from mass times gravity. So if they give it to you in the question in newtons, it is already the weight. If they gave you something as a mass in kilograms, you would need to either times it by g or by 9.8, whether you prefer to use the full numbers or you're happy using letters. The block isn't about to be dropping straight down though. It's not pushing its way through the slope, it's going down it. So we need to find the component of this weight that we say is parallel to the slope. For this, we're first of all going to create a dotted line that is perpendicular to the slope, that is to say at a right angle, and then we'll do one that is parallel to the slope down here, making this a right angle triangle as well. Now, if this angle here is 26 degrees, and this would be a right angle like so, because it's coming straight down against the horizontal ground, this here would be 90 minus the 26, because these three all have to add up to 180. You've already used up 90 here, so then a further 90 minus the 26 leaves you with 64 degrees here. However, because this is a right angle on this side of the dotted line, this must in total be a right angle here. So again, this must now be 90 minus that 64, bringing us back to 26 degrees. So basically, whenever you draw this right angle triangle here, whatever the angle of the slope is the angle that you will find in here between these components. Now we can work out what the magnitude of the individual components are. So again, we can imagine that you have this part of the weight is pushing the block into the slope, and then this part of the weight here is pulling it down the slope. This is essentially just trigonometry at this point, where the 10 is the magnitude of the hypotenuse of the resultant. So here then, this would be 10 sine 26. Because this is the opposite, that is the hypotenuse, and you rearrange as you do in trigonometry, and this here will be 10 cos 26. So the 10 sine 26 is the part of the weight that would be pulling the block parallel to the slope. So we can imagine that that force there is acting directly on the block this way. That is your forward force. So 10 sine 26. But because it's in equilibrium, this will then equal the reverse force, the backwards force. Right now, we don't have a backwards force labelled on here, but that's because we haven't labelled every force that's on this diagram. Something else we need to add is the normal reaction force. So the reason why, again, this block isn't just pushing straight through the slope is because the slope is pushing back on the block. Specifically, it's going to be pushing back perpendicular to the slope, not just straight up to counter the weight. So this reaction force here, this R, this is a variable force. Its number can change depending on the other perpendicular forces to the slope. In this case, the only other perpendicular force is the 10 cos 26. So the R just has to have that same value in order to balance the block, to make sure the block isn't, as I say, falling through the slope, but also not flying off the slope. R will be whatever is necessary to balance it in that perpendicular direction. What we can then have, which is then per the actual instruction of the question, find the coefficient of friction, we have some frictional force. Friction always acts in the opposite direction to motion or desired motion. So, if the block is on the point of sliding down, friction must be acting upwards and being what's holding it in place. We can calculate friction as being a coefficient of friction, which is just a value that any material has that describes how much friction it generates, times by the normal reaction force. So here, because we know the normal reaction force is going to be 10 cos 26, so this is going to, and the coefficient of friction has this symbol here called mu, it's a Greek letter. Normal reaction we can just say is R. So we'll say it's mu times that normal reaction of the 10 cos 26. There are now no other forces at play. This is our entire expression. To get mu on its own then, we'll just divide across the 10 cos 26. The 10s are going to cancel. And from our trigonomic identities, we can say that a sine of one angle over cos of the same angle is going to be the same as tan of that angle. So tan 26 equals mu, and if you were just to put that into your calculator, let's just say to 3 decimal places, you would get 0.488. Now yes, your coefficient of friction is usually going to be between 0 and 1. There are the rare occasions where it can be greater than 1 if it's a really rough surface, but yeah, usually you're looking for it to be 0 point something. And as I potentially just alluded to there, one thing to look out for to make sure that we are dealing with friction is in the description of the question, it describes it as a rough surface or a rough slope. They may well then also just mention coefficient of friction explicitly, just to make sure you're pointed in that direction, but either way, to make sure, look out for that word rough rather than smooth. If it's smooth, then you can ignore that whole frictional element entirely. What if, though, we had some other forces acting on our object on the slope? Over here, we're saying that we have a brick weighing 10 newtons again, and it lies on a rough plane, there we go, and is in equilibrium on the point of slipping up the plane this time. Well, how could it possibly be point on slipping up the plane? Well, that's because we now have this 12 Newton force applying horizontally to the right on it, and that is going to have its own components, just as how the weights have components, that is trying to push it up. If we're going to start just by labelling all of these forces, therefore, before we get to the actual crux of the question, just because it's good to make sure we have everything understood first of all, we can say that if it's got a weight of 10 newtons, then yeah, once again, we have this 10 newtons coming straight down, and from this we can create our right-angled triangle, where that is now going to match this 30 degrees here. So this is going to be 10 cos 30, and this would be 10 sine 30. You then have your normal reaction force. We're not going to give a label to that yet, because first of all, we also need the components of, let's say, this 12 Newton force here. These components are again going to be, one is parallel and one is perpendicular. This angle here is also going to match whatever angle is here, because this is alternate angles. The 12 Newton, if it's coming straight to the right, is parallel to the ground, and this line here is meant to be parallel to this line here, so it's the equivalent of a Z angle. So either way, whatever this angle is, this angle will be here too. So we end up with 12 sine 30 and 12 cos 30. On top of this, because it's moving upwards on the point of moving up the slope, friction is now going to be acting downwards, and that's going to be our mu r, because we don't know what either of them are yet. With that, those are all of our forces, so let's see what it's asking of us. Find the coefficient of friction, then, if the 12 Newton force is removed, determine if the brick moves. Okay, so like what we had previously on the left, because we know it's on the point of slipping, it's not moving yet, it is in equilibrium, so the forces trying to push it up the slope equal the forces trying to pull it down the slope. Well, the upward force is going to be just that 12 cos 30 here. You may know that cos 30 has a value of root 3 over 2. So 12 times root 3 over 2, if we want, we can just already simplify as 6 root 3. And then, because that's the only force trying to push it up, we're now going to say that equals the 2 coming down. First of all, we have our 10 sine 30 here. Sine 30, again, if you know, because we're going to be in degrees, is a half. So 10 times a half is just going to be 5. And then we'll add to that the friction here. Now, for your reaction force here, we're going to have not only this 10 cos 30 here going downwards, but also this component of the 12 Newton force. Both of these are acting to push the block into the slope. So if the reaction force is looking to balance in the perpendicular, it must equal the sum of those two. So we're going to have our mu for a coefficient that we don't know, then that will be times the sum of 10 cos 30, which again, if cos 30 is root 3 over 2, 10 cos 30 will be 5 root 3. And then we'll add to that the 12 sine 30. Sine 30 is a half, so 12 times a half is 6. At this stage, we have almost exactly like what we had over here, so we'll just rearrange to get mu on its own. So we'll minus the 5 from the 6 root 3 to begin with, and then you can divide by this bracket here. Putting that into your calculator, again to 3 decimal places, you get a coefficient of friction of 0.368. Now that we know this coefficient of friction, we can move on to the second part where the 12 Newton force is removed. So, as with any mechanics question, when the situation changes, you want to rework out your model. You don't want to assume that anything is automatically the same. In this case, the components of the weight, well, they are going to stay the same because it's still a 10 Newton brick. However, your reaction force is now going to change because you don't have that component from 12 coming into it. Now it's just going to equal the 10 cos 30. But that's not the only thing that's going to have changed. If you have removed that 12 Newton force and there's no longer anything in that moment pushing it up, the brick is now going to want to move down the slope. Yet if now its desired direction of motion is down, that means friction is going to have flipped. Friction is now going to be in the upward direction. So, as I say, we can take the this component of the weight going down the slope as still being 10 sine 30, which will still have a value of 5. But now that's the only force trying to pull it down the slope, so it's at this stage that we'll go on to compare with the upward being the friction. We don't know yet if it's equal or if it's some other inequality sign, because the whole point is we're determining, does the brick move? We're seeing, does this weight here get matched by the friction or not? Actually, I just want again to clarify at this stage, just like the reaction force, friction is not a fixed number. It has a maximum value that it can reach depending on what's trying to pull it forwards. The friction would never actively be greater than any forward force or overall resultant force. because that would be suggesting that the object just spontaneously moves in the other direction by touching the surface. So if this frictional value actually ended up being greater than the 5, then we're saying that's the biggest theoretical value it could have, and it would actually just reduce itself to be 5 in this case. But anyway, we don't know, we need to check that. So on this other side of our currently unknown sign in the middle, we're going to have our 0.368 times by, and again, the reaction force is now just this here, which is going to be the 5√3, and that here has a value of 3.185. So this is certainly smaller than the 5. Therefore, the friction, even at its maximum, is not strong enough to overcome this downward component of the weight. Therefore, the brick will move downwards. If we're right with that, and we can see how we need to construct triangles such as this to get components of forces that are either parallel or perpendicular to the slope, how then we can generate our friction and so work out either resultants or other elements because of an equilibrium and so forth. If we're all good with that, let's just see how you would get along with an example of your own. What if you were presented with a question such as this? So you have now another slope which again is at 30 degrees, but now the particle P has a further force being applied to it up here, which is in turn at 30 degrees above that slope. The particle P has a mass of 4 kilograms and is moving up the rough plane with a constant velocity of 16 meters per second. Now find the magnitude of the normal reaction force, the value of mu, and then, if the 36 Newton force is removed, find the distance that P travels from the instance of removal to when it comes to rest. Again, you'll just want to think about what forces are acting where, what components may be necessary. Also think what the implication is here of now being told it's moving at a constant velocity. Pause the video, have a go for yourself, maybe just checking back to the previous examples if need be, and then press play again when you're ready to compare. So, as before, we'll first of all just want to draw on our various components. So to begin with, we'll say, okay, the weight is going to be coming straight down, but here we don't know the weight, we just know the mass. So we can say that this here the weight would be 4g, or 4 times 9.8. Again, depends on what you prefer, doing a decimal or doing it with the letter. We're going to want the components of these though, so we'll make a right-angled triangle like so. This is going to be 30 degrees. Like before, sine 30 for this side is going to be a half, so a half of 4g, which is going to be 2g, and here the cos 30 is going to be √3 over 2, so that times by the 4g is going to be 2 √3g. Then this force here for the 36 newtons is going to have components of its own, so again we make a line that's perpendicular and one that's parallel. So this time it's going to be trying to lift the particle up from the slope as well as pulling it up here. This then, for the sine 30, again half, just makes this 18 newtons, and this here is going to end up being 18 √3. Because the particle is moving up the slope, that means friction is acting downwards, so that's going to be our mu r, and because that r is going to be related to just the reaction force here, we should label that on as well. Now that we have all of these forces, we can start constructing equations. Because it is moving at a constant velocity, that means that it has no acceleration. And if it has no acceleration, it has no resultant force, because again, the resultant force equals mass times acceleration. It has a mass, but then timesing by that acceleration of 0 negates it all. So if it has no resultant force, that means the forward force equals the backward force. It is in equilibrium. Again, equilibrium doesn't necessarily mean it's not moving, it just means it has a constant velocity, which may sometimes be a constant velocity of 0. So the forward force trying to pull this thing up the slope is the 18 root 3. That is the only force trying to pull it parallel up the slope. So that is then going to equal the combination of the 2g coming down here plus this mu r. So that's going to be mu here, but timesing by the r. This time, there is going to be some combination of the other perpendicular forces. But this time, because the 18 is also lifting up off the slope, it's alleviating the balance here from the downward force. So it's just the 2 root 3g would equal instead the 18 and the r together. Therefore, the r is the 2 root 3g minus the 18. From here, all we need to do is rearrange like we did last time. So we're going to have the 18 root 3 minus 2g over the 2 root 3g minus 18. That's going to give us mu, which to 3 decimal places is going to be 0.726. So we have our mu. We now know that that is going to be the coefficient of friction throughout the rest of the question. I'm then told if the 36 Newton force is removed, okay, let's get rid of that from our diagram therefore. Find the distance that P travels from the instance of removal to when it comes to rest. So just like when we're dealing with questions that have objects moving in the vertical, such as with pulleys, just because you remove a forward force, like you remove the tension that's pulling the thing upwards, that doesn't mean that object immediately starts falling in the downward direction. It still needs to decelerate to a halt to reach a greatest height. So P is still moving with some velocity up the slope at this stage before it then comes to a V of 0, which is when it comes to rest, after which it would then potentially start rolling back down the slope. We don't know. You would have to then do the same calculations as the previous question, see if it moves or not, but that's not the point here. Because P is still moving upward the slope, friction is still going to be in this downward direction combined with the down component of the weight. As there is no forward force, however, active forward force, the resultant is just going to be this minus the 2g minus, and now the r is just going to be this 2 root 3g, so 0.726 times 2 root 3g. Together, that resultant force will be the same as the mass times acceleration, F equals ma. So the particle has a mass 4 and then an acceleration that we're now trying to find of a. It now has an acceleration. By just putting this into your calculator and then dividing by 4, this leaves you with an acceleration of approximately 11.06 meters per second squared. How can we then use this to find the distance? Well, it has the word distance here. Previously, we were just mentioning velocities. We now have an acceleration. This is where we come to our Suvat equations. So we can say here that the S is what we're trying to find. The U is the 16 before, because it was traveling at that constant velocity before anything changed. V is going to be 0, because it's coming to rest. And A, yes, here, well, what should, strictly speaking, have just been minus 11.06, because that's in the backwards direction. From here, we can use the equation v squared equals u squared plus 2as, just rearranged. So S is going to be v squared minus u squared over 2a. So 0 squared doesn't make a difference, so just minus 16 squared over 2 times minus 11.06. This gets you a distance that will travel before resting at 11.57 meters. Now this may seem like quite a long way for this particle to be traveling, but you also have to acknowledge this thing was moving 16 meters every second. So this must have been a pretty big slope to start off with. If you're happy with that, you can see how we got to that answer by changing the model and then getting the values we need for a Suvat. Let's just have a go at one further question, which is actually now going to combine the slopes and the connected particles from a previous video. So as we can see here, we've now got more of a pyramid shape kind of thing here, or triangle, with a pulley on the top, and then two masses, two particles, one on either side. A has a mass of 3m, and B just has a mass of a singular m. We don't know what m is. 3m, the A, is on a smooth surface, while B, the m, is on a rough surface, meaning it will be experiencing friction, and both have an angle of 30 degrees. As we go through the description then, it's just going to be giving us that same information basically. The light inextensible string, telling you that the acceleration is going to be the same for both particles and that you don't have to consider the mass of the string itself. We are then told, so the coefficient of friction on the right-hand side is just going to be mu. We don't know what mu is yet, we're going to have to be working it out. And then the string is taut, so there is tension in this string. So when the particles are released, A is going to move downwards and B is going to move upwards, which makes sense because A is the heavier mass. And we're told that the accelerations of A and B each have a magnitude of 1/10 of g. So by considering the motion of A, find in terms of m and g the tension in the string. Okay, so we know that our answer is going to be in terms of m and g. We don't have to worry about the fact we don't know what m is, and we can keep g as g rather than 9.8. And it's specifically getting us to focus on this particle A first of all. In general, though, we should probably do a job of just labelling all the forces as before, just to make sure we've got everything in mind. So we've already acknowledged we're going to have tension in the string. So tension is going to be going towards the pulley in both cases. As for the components of weight, so the 3m here, that's going to come down with a weight of 3mg, which if we then do our right angle triangle with angle 30, it's going to leave us with this component being 3/2 mg, because again, sine of 30 is a half, and then this here will therefore be 3√3/2 mg, because it's at 3 mg times by √3/2, which is the cos 30. There is going to be a reaction force as well, which you can put on if you want, but because this surface is smooth, we're not going to be using that value for the friction, so it's not as important. As for B, again, that's going to have now a weight coming down. That's just going to be of mg. So then for its right angle triangle, which will also have an angle here of 30, that's going to leave this just being a half of mg and 3√3/2 mg. It, though, will have an important reaction force, because that will then lead to the friction going down the slope, because B is moving up, of mu r. These now are all of the important forces. So we can turn our attention back to specifically what part A was saying. So find in terms of m and g, the tension in the string, based solely on A. So we are just going to look at A at this point. Because it's moving down the slope, this component of its weight that's parallel to the slope is going to be our forward force. So the 3/2 mg, that is going to be minus whatever the tension is, and that will equal the mass times acceleration. So the mass of 3m times by, and we know that the acceleration is 1/10 of g. So if we were just to switch that around, we would end up with 3/2 mg minus 3/10 mg equals 10, which you could just work out to be 12/10 mg, which, if you prefer, 6/5 mg. Then we can go to part B, which will be by considering the motion of B, find the value of mu. We can do this now because we have the tension. Previously, that would have been two unknowns. So here, because B is moving upwards, T is going to be its forward force, but then we're going to minus from it this mu times by, and the reaction force in the case of B is just going to be matching that perpendicular component of the weight. So it's just going to be that 3√2 mg here. And yet you'll also then take away this component of the weight here, because that's also acting back down the slope in the opposite direction to the way it's actually moving. So also minus 1/2 mg. and this will ultimately equal then the mass times acceleration. So the m times, and again we know the acceleration to be a 10th g. So if we're at this point looking to work out what mu is, we want to add that term onto the other side and minus this one over here. So you'll get that, well, the t we know is the 6/5 mg minus the half mg, now also minus the 10th mg, equals to mu root 3/2 mg. So to get the mu on its own, we'll have, so all that left-hand side, so the 6/5 mg minus the half mg minus the 10th mg, all over root 3/2 mg equals mu. All of these mg's, because they're in every single term as a common factor, are going to cancel. So now if you just put into your calculator 6/5 minus a half minus a 10th and divide all that by root 3/2, you get a coefficient of friction finally of 0.693. As I said, something we can expect it to be 0 point something, and that still holds true even in this slightly exceptional question, which combines basically every concept that we have covered in this chapter on F equals MA.